Oh, really?
Hi, Sam.
It was like a smiley thing.
Well, can you fix that, please? Thanks.
Why
Okay,
does it say
so
equals
what if
They have to
I
equal
were
it.
to draw things like this, like from the beginning of class? Let's say we have two objects and, okay, so let's say object number one has velocity vectors and it has acceleration vectors, and they're on two different graphs. Okay, so object one is blue.
Should we write this graph?
If you understand it, there are lots in tests that you have. Oh, but that's not very smart.
I remember doing that.
Let's see, so. Okay, so so the blue object has this velocity vector and this acceleration vector, and the orange object has this velocity vector and this acceleration vector, as seen by the label on the graph. Which object is traveling at the largest magnitude of speed?
The blue object.
Why?
Because it's speeding up.
Which one is currently traveling at the largest magnitude of speed?
Oh, never mind. The orange one.
The orange one, because literally the arrow is bigger, so that means the velocity magnitude is bigger. Which one is speeding up?
The blue one.
The blue one is speeding up, why?
Because it's really
going
big.
in the same direction.
No, not because it's really big, because its velocity and its acceleration vectors point the same way. If you're speeding up in the same direction at which you're going, then you're speeding up. But if your acceleration vector is opposite, or in any way sort of opposite your acceleration vector, then what's happening to the orange guy?
It's slowing down slightly.
Just a tiny bit of slowing down, because the acceleration vector points in the opposite direction of the velocity vector. Let's see. Which one is accelerating more quickly?
The blue one,
Why?
because it's bigger.
Yes, and truly, if I did it differently, if I said, which one is accelerating more quickly?
The orange one.
Yeah, even though it's like totally slowing down, its acceleration has a greater magnitude. So it's accelerating more quickly, but in the opposite direction it's traveling, so it's slowing down. It's just doing it quickly. Crazy, huh? So think about the lab that we did where the car went off the end of the desk. Okay?
Oh, that one.
So think of your X direction and your Y direction. What's the equation that was really big in that lab? Because this is a big important
For what?
equation.
For
For
this.
the car going off the end of the desk.
But what's the equation
Yeah, that's
called?
the question. Let's see.
Called? I can find it if I want.
This is a big important equation. Okay, so delta X, what does delta X mean?
Change of that.
Changing
what's
displacement.
Displacement. So the change in displacement, which could be in the X direction or the Y direction, is equal to initial velocity times time plus 1/2 acceleration times time squared. So, if that car scooches off the end of the desk, what is its,
Wait, does that mean we have to write that? What's the F equals?
that's
already
the
did that.
seesaw equation,
Oh,
torque. You definitely need that equation, but we're talking about car, which is this. So when the car goes off the end of the desk, we have stuff happening in the X direction and stuff happening in the Y direction. So remember, every good physics student breaks
equals
down
M.
any vector into its two components, X and Y, so that you can study it. what happens to that car when it leaves the desk in the X direction?
It
So-
goes down.
Well,
And the
it
X-
becomes 0.
Oh, sorry.
X direction.
Never mind.
So what's 0?
It becomes 0, like the.
It's
Okay. So in the X direction, what's acceleration of that car?
9 point. No.
0.
0. There's
Zero.
nothing acting upon it. So you have an acceleration of 0. How about acceleration in the Y direction?
9.8. 32 feet per second squared.
It could be, but no feet. I promise.
Okay.
Last year I promised him that, and I put one that was, I had to change the final right in the middle of class because I left a English unit on.
One of the tests I didn't know what it was for.
I
feet, and
remember
I
you had the
converted.
most crazy conversion, but you were right. What is initial velocity in the X direction? Initial velocity in the X direction.
Whatever you
get
push.
pushed.
Right, so that's usually what you want to find out. Usually what you want to find out. In this case, I think it will be. What's initial velocity in the Y direction?
0.
0. When it leaves the desk in the Y direction, it has no, hopefully, time. Well, let's talk about displacement. So what's the displacement in the Y direction?
You don't know.
Whatever it is that hit the ground.
Hopefully I'll give you that. That'll be the height of the table or whatever cliff it's falling off. So delta X in the Y direction will be cliff height or table height. And delta X in the X direction is what you have to measure. So that's why we laid the ruler on the ground so we can see where the car hit. So where object lands, distance from cliff. And you have to measure something here. Now, we usually do this without measuring time, but we usually have enough to get time in one of the two directions, right? So if we solve for time in the Y direction, of course that equals time in the X direction because the X and Y hit the ground at the same time and stop, hopefully. So solve for time in the Y direction, plug it in here, then you can find velocity in the X direction. Just make sure you know where the zeros are, okay? In the X direction, you have 0 acceleration. In the Y direction, you have 0 initial velocity. So make sure you know that equation. Solve for time in the Y, then you can find what you need in the X. So what affects the amount of friction something experiences? Why is it
What's
easier to
on?
push the pen than this thing?
Because
Oh,
it
Weight.
Wait.
Okay, so mass or weight, definitely a big one. So this, which is weight, right? What else?
What it's on, like with the substance.
Okay, so roughness,
Like if it's ice or sandpaper.
right. Roughness or smoothness of the two surfaces that are interacting. And why is that? What do you see at the,
'Cause
even
they
on something very smooth feeling, what do you
get in
see?
and then they, I don't know.
The attraction between the molecules or the molecules.
Okay, the surfaces have two issues. One, even very smooth things, when you get down to the molecular or atomic level, they have little bumps and grooves. So the thing that you're trying to move also has little bumps and grooves, and they interact by crashing into each other, and you have to overcome the, the collision of them with each other. Also, there's an electrostatic attraction that every atom has a little partial charge, which can change, but and it'll change based on what it's near, and it'll have little interactions that attract or repel. So you'll have those forces. So you have to overcome physical barrier plus electrostatic barriers to overcome friction and move something. What else affects friction? How do you compare the coefficient of static friction to the coefficient of kinetic friction?
Well, if it's moving or not.
Okay, so if something's already moving, it's experiencing less friction than if it's stationary. There's the 3 factors, really 4 if you count the physical and the electrostatic interactions at the atomic level. But those are the things that affect friction. We talked about that. Talked about that. I don't know what that is. Let's see. So, there is a problem, which I'm actually going to look up because I forgot to tell them last year and I got all kinds of crazy answers. So I'm just going to mention, you might want to check out on your own, which of course we never went over in class, but is a fascinating problem. I think it's 9-9. Yep, on your own, 9-9. Chapter 9, problem 9, on your own.
That's nice.
Yes.
Of the 10 questions, are they all gonna be math questions?
Pretty much.
Okay.
I'll even take out a copy of the final and look at it here in a minute. Let's see. So, we talked about that. Waves. What kind of wave is a sound wave?
Transverse wave?
No.
What kind of wave is a sound wave?
Sound wave isn't oscillate, or the one that's like a slinky.
Slinky, so this is a longitudinal wave. Well, I should probably draw it with something. So waves of course have areas where they're denser, areas where they're more spread out. Okay, so if we assume that we've got a dense area to a dense area there. So dense, spread out, dense, spread out. I'm bad at drawing those. So what would you call the distance from the beginning of one dense area to the beginning of the next dense area?
The wavelength?
That's a wavelength. And in a sound wave, what does wavelength affect?
How loud?
What is that right underneath that little bar thing? I can't-
This is a lambda. It stands for a wavelength. That's the worst lambda ever. It's getting worse every time I mess with it.
I'm gonna just write
Did
wave.
you say it's longitudinal?
This is longitudinal. Sound waves are longitudinal. The distance from one, what is this, like compressed area. This is a rarefaction. This is a compression. So from one beginning of one compression to beginning of next is a wavelength, lambda. And that affects what characteristic of the sound?
Pitch then?
Pitch. Wavelength affects pitch. And what does affect volume?
The amplitudes?
Amplitude. So the amplitude is the height here. That's amplitude. And this affects volume. Okay, what kind of wave is a light wave?
Transversal?
Transverse. Light wave is a transverse wave. Give it an axis. Okay, so here's a transverse wave that's more like a light wave, although light may be a particle, kind of a wave, that wave-particle duality of light thing. The wavelength is from crest to crest or trough to trough. And what does wavelength affect in light?
The brightness?
No,
The
Color?
color. So wavelength is color. What does affect brightness?
amplitude.
Amplitude, so the height. amplitude is brightness. Okay. So, I don't think there are
So
any
does it say
math problems.
Amplitude is,
Brightness. The amplitude of a light wave is brightness. Now remember that light waves are electromagnetic radiation. So if this is the
you said there's
electro
no math
part,
problems in this?
no light math problems, then remember the magnetic wave part of light would come in and out. Okay, so remember also that sound waves travel, let's see if I can write it down. Sound waves travel parallel to direction of propagation. So if a light wave is oscillating this way, it's also traveling that way. Sound waves travel perpendicular to the direction of propagation. So if it's traveling this way, it's oscillating perpendicular to the direction of travel. Perpendicular to travel. And remember, there's a third axis for light waves, where you've got the electromagnetic direction of travel, all three perpendicular to each other. Have to have a 3D chalkboard for that. How do you charge an electroscope? If I want to charge by induction, what do I do?
You bring something close to it.
Induction, yes,
Can't
close
touch
to.
it.
But I am touching it, but how?
Your finger?
Well, I'm touching the other part of the electroscope with my finger, yes. So the charged thing for induction comes near but doesn't touch. But there has to be a pathway for the electrons to escape. That's my finger. Then I remove them both at the same time. Now, if I have a negatively charged rod and I use it to charge by induction, then what kind of charge will I impart to the electroscope?
Positive.
Positive?
Yes, the two foils will become positive. Why? Did they get
Because-
extra
Because-
protons?
Well,
No.
it,
No.
You
it pushes
scared
into
all
the finger
the-
or whatever.
Okay,
Um,
so it drives the electrons away because the rod is repelling electrons. They want to get far from it. That means there are fewer electrons than protons, so it has a positive charge and repels. If I want to use the negative rod to impart a negative charge, how do I charge the electroscope?
I just touched it.
Conduction.
Conduction, by touching it. So I literally touch it with the rod, forcing more and more electrons. They fill up the foil with too many electrons compared to protons, so the foils become negatively charged and repel. In both cases, of course, the foils repel each other. If you charge with a negative rod by conduction, you give it a negative charge and the negative foils repel. If you charge with a negative rod by induction, then you give it a positive charge because electrons are leaving and the positive foils repel. Both cases you're touching, but only in conduction are you actually touching the electroscope with the charged rod. By induction, you're touching it with something that can conduct the electrons away, but the charged rod does not actually touch the electroscope for induction. How about the egg drop lab? What did we do to protect our egg?
You had to slow down the speed of the collision and reduce the force and impulse.
Okay, so impulse, that's important. What's the equation that you would use for an egg drop situation or an airbag situation?
It's like,
I really hope all of this is on the test, because I'm sorry.
It really is all on the test. Egg drop lab. Impulse.
zoom impulse, like go with the momentum. It's
Okay, so
mass and velocity.
momentum and
I don't remember.
time.
I did
I
write that
actually have
lab
to-
this morning.
Delta P equals F times delta T. That's what it says in the book.
Okay, that's a good equation, I like that. Okay, so we have our momentum, our force, and our time. Now what can we control?
Your time.
You can control time. How do you extend the time over which the collision takes place?
By making it like the
Fle-
impact.
well, if it's like
less
flexible,
impact.
well, like the airbag, it's not like you just smack into it right away. It
stop.
slows you down.
Right. Okay, so we control time by when the collision occurs, the egg just hitting the ground. How long does the collision take? Right now.
Right away.
The egg encased in something soft, that something soft hits the ground, the egg can keep moving over a period of time. It experiences that force, the same force, but over a greater time, because it slows down more gradually instead of instantly. So if you increase time, you decrease the impulse. It experiences that force over time, and then hopefully your egg doesn't break. So be ready to discuss that, since some people still haven't turned in their egg drop labs.
I just did this
Good.
morning.
I did. I know I did.
That's why I remembered all it, because I was looking at the book this morning.
But yeah, look back over if you did turn it in and make sure that you understand all your comments on it and that sort of thing. Let me see if I have a copy
Mine
of the
broke.
final somewhere.
If I
I'll
had more
make sure I
time,
told
maybe.
you
I didn't
everything.
get to make it for sleep.
I did.
Uh,
I did.
Canadians.
Nothing on circuitry or magnetism because you guys just did that. Surely you remember it by now. Opening Josh's final, possibly.
Where's he at?
Florida, I think. That's my chemistry too.
Can you believe it's
Oh,
already
here's the
May?
physics one.
May 8th.
Normal force.
Wait, what
What's
is the-
normal
the
force?
final
It's the
do again?
opposite of what, it's like when you're staying on, like if you're staying on a board, the force exerts like the opposite direction of.
Okay,
Right.
normal force is the equal and opposite force that the thing exerts
So it's
against.
just your weight.
It's equal and opposite to your weight. Your weight is the force down. The equal and opposite force to your weight is the normal force, in obviously opposite direction. Make sure you have definitions for simple harmonic motion and uniform circular motion. Let's see. Did that. Did that. All right, I think we've talked about every single thing. Any questions? Anything I said in that speediness that went?
Is there gonna be a lot of math, like, or is it just gonna be like kind of like review questions?
It's a lot of lab discussion.
Oh yeah, I like those. I hate math
It's not-
questions.
Oh, here's the math page. Hold on, I didn't look at this page.
Oh, great.
One math problem about the toy car, lab 4.2. Toy car goes off the desk. Use that equation.
Writing that down. Which equation? The EF one?
Yeah.
Yeah.
Well,
When you have friction, where does the wasted energy go?
Into making the molecules of the object exerting friction, like making those molecules speed up. Or
When a molecule speeds up, what happens?
Is that 4.1?
Exactly, molecules speed up.
So
But
is it?
a speedier molecule is what? kind
more
of
kinetic energy.
molecule? And a molecule with more kinetic energy is?
a movie one.
A molecule that's moving faster is hot.
Oh.
Friction makes heat.
Oh, okay.
Yeah,
Writing that
the
down.
chemistry way of saying heat is the molecule is moving faster. But we'll just say heat around here. There's a seesaw problem. and there's a discussion just like lab. What's the washer swinging around lab? I don't remember off the top of my head.
The toy car
I
one was
failed that so many
4.1, right?
times. 7.1.
We'll talk about that right now, in fact.
Ugh.
And on your own problem 9.9, a problem similar to that, but no real math. You have to write
Lab
the equation.
7.1.
On your own 9.9.
Oh yeah. Hey.
Okay, then the last thing would be,
I mean, I want to have them. Maybe. Oh wait, are you done with them?
No, I just haven't done it yet.
Oh,
okay, so if
never
I'm
mind, you can
swinging my
keep them.
washer around, right? I'm trying to keep my speed constant, right? We really tried hard to keep our speed constant. We kept the mass constant because it was just the one washer that was traveling in the circle, okay? So our variables were either centripetal force, which was provided by 1, 2, 3, or 4 washers, depending on how many we tied on the end, and the radius, which was how long the
Was that
string
radius squared or no?
was. No,
And that's 7.1.
right. So when we varied the radius, we held the washers constant at 2, right? Oh, and then velocity, of course, changed. So if radius, let's see, as radius increases, velocity.
Yeah, I know. I need a way more stress.
As radius of the thing increases, velocity does what?
Decreases.
Velocity as radius increases, yeah, velocity decreases.
Are you sure?
Well, because if the string is getting longer, then it's gonna take longer.
But that's,
But I don't.
But it decreases
Not velocity.
velocity.
you have to consider the size of the circle, the circumference.
It stays the
You have to
same.
consider the distance.
Does it always
travels.
stay the same?
No.
Does it
Look at the equation.
increase as well?
Let's rearrange the equation here. FC times R equals M times V squared. So if we're holding the force constant by keeping the number of washers the same, we're holding the mass constant because it's the one little washer flying around. If we increase R, what's going to happen to velocity?
It's gonna increase exponentially.
Yes, velocity's going to increase. I don't even care about the exponent, it's just going to increase. As the radius increases, if these guys are constant, the velocity has to increase. Okay, and our other variable, when we varied the force, right, we held radius constant by making sure we use just like the red line every single time. Mass is always constant. So when we increase the force by increasing the number of washers, what will happen to velocity?
It'll increase.
Mm-hmm. So they vary right with each other every time in this lab. As radius increases, assuming, and I'll even write, force and mass are constant. And down here, we have radius and mass are constant. Okay, so if force and mass are constant and the radius increases, velocity will increase, because you can see there's a direct relation except for that exponent. As force increases, assuming that radius and mass are constant, then velocity must also increase. And that does seem counterintuitive, but what you're not seeing is that velocity isn't just how long it takes to fly around, you have to consider the distance it's going. So as radius changes, it's going a bigger distance, and it really is speeding up as radius changes. It's just going further, so it seems slower. But that's everything on the test. Do you want to do a practice seesaw problem or a practice car problem? How much time? We have time to do it, and then that's one thing you don't have to worry about.
How about we start one of the
We should.
extra quarterly?
You can work
Do
on
we
quarterly
actually
tests.
have to take them?
Yes.
Like-
Yes, your mother has to sign off that you did them.
Because I wanted to like study like crazy and like take this like this week or something like that.
Well, you can take the test and then do the
Oh,
extra
okay.
practice or the extra quarterly test if you really want.
Well,
Will the quarterly test actually help us on the final?
possibly. I think the
I
lab,
feel
like
like
the
it
labs
won't
help a lot.
really.
It might not, but it will help cement all of the concepts in your head for the year,
So
which
we
is
have to take them.
yes, the purpose of taking a final isn't to get a grade. The purpose of taking the final is to have one last review so you really remember
It's about
everything.
learning.
It's about
About
learning.
getting an A or B. Okay.
No, it isn't.
But it's about learning.
Or maybe a high C.
It's definitely not about getting an A or a B. It's about
Or a high C,
remembering
don't forget.
physics so you don't suffer through college. Not taking physics in college is what she just said. in her
No,
head.
I didn't.
Aren't you
I
required to
just
take,
said,
like, an
oh.
intro
I
physics?
said,
Aren't you required to take like an intro
No.
physics?
No, unless
You
you're an
crazy?
engineer.
No, that's it.
If you're gonna major in history, the physics department does not
Yeah.
want you to see you ever again.
Yeah, this is.
But
You'll be doing
Physics.
I mean, if you don't
I will
want
be
it,
better
Physics,
prepared for
history,
life.
geography.
yeah,
My children are on a seesaw. I can.
you can homeschool your children successfully if you learn something in physics. You won't have to pay somebody to do this.
I'm joking.
So here's a seesaw.
Kids could
Let's put.
I
Let's
think it'd
see.
be like punishment.
Die.
I
It'd be like
have.
punishment to send your kids to public school.
I'm not saying it until
I went to public school when I was in elementary school.
no wonder.
I went to public school until I was in 7th grade.
I'm sorry.
Yeah, I know.
This guy's stuck in the wall, right?
Yep. I was like in
See what they
3rd or
teach you. It's okay,
You won't
children.
get shocked too bad.
fourth.
It won't hurt that. You won't die.
Hopefully the teacher doesn't find out. When she sees your face, your head, and your hair
Alright,
sticking.
I have 3 disgusting cats. Misty, Corey, and Belle.
Do you really have-
I do, and they're disgusting.
How are they disgusting?
Because their cats are gross and furry and smelly.
My uncle says the only
I'm
good
allergic
cats
to
are
cats.
dead cats.
That's what my dad said.
Really?
Yeah.
And he.
I kind of like them, but I don't like cleaning up after them at all.
Grandma had it.
Oh, you're good.
She had like 9 cats.
Okay.
I actually had one because they all died.
Lance Kelly's cat is so cool.
My cat, I have one really cool cat, but he's old and gross. Okay, so, I've got these 3 cats. If I put Misty on the end of the seesaw and Belle on this end of the seesaw,
She
let's
has to
see,
kill
the
'em.
seesaw is 5 meters long. And the fulcrum is right in the middle. And we'll give that 3 significant figures just for fun, so we actually get a real answer. And let's give these guys a couple of significant figures also. So, so where should I put Corey so that the seesaw balances?
Wait.
We
In the
have
middle.
1 meter away. Is that the answer?
I don't know, I just made this problem up.
Oh, okay. Let's see if I was right.
I doubt it's an exact.
1.00.
I gotta fill in this. It's gonna be a
R is a
hard
radius.
test.
I'll do it on this paper over here, I suppose.
what happens if you don't do
weight.
good on the final, but you do decent on the tests and the labs?
The final is 10% of your final grade. You'll do
Basically,
fine.
if
Can
you
either
fail,
help
you
a lot
get a-
or mess you up.
Even if you get a 50, you get 5% out of the 10% it is. And if you super fail, I'll even let you correct it.
Really?
Like if it's gonna make a big difference in your grade,
You let me correct it?
I will drag
Because
you
the
through
point is
corrections.
learning.
The point is learning in this class.
I do like
Never
learning.
forget it.
Who likes learning now? I actually do like learning. Not really.
You said just not physics.
Wait,
Oh, at least at least if I do pass at the end of the year, I'll be like, yeah, I passed physics. Yeah.
Honk if you passed physics. That's physical chemistry, by the way. They actually make the bumper sticker.
And then it says I passed physics.
Honk if you pass P-Chem. Nobody will ever honk at you. Like 2 people in the whole town. Although around here with engineers, maybe more. So Corey's 4.
I was talking about like
kilograms.
physics, like.
And
this
one
class.
time, funny honking
It's the
story.
physics of
I
chemistry.
put a thing on my
and
brother,
it's
back of my brother's car
horrifying.
that said
Have you
honk
done it?
because it was his
Oh,
18th
yes.
Did
birthday.
you pass it?
2
And he said
semesters.
I'm telling
Did you
you
pass
the
it?
story.
I got an
So
A
he
in
was on the way to
physics.
Suicide, and he said a ton of people were
Ow.
honking at him, and he didn't know why. And it was so funny.
funny.
And then he got really
Oh,
mad.
5 minutes.
Well, hurry up then.
We're not listening to my story.
no, that was so funny.
It was. I'm gonna do it to you when you get a car. And you won't know why all those people are honking at you, and then you'll be like, oh, because they put a sign on my car. But it'll say honk if you think I'm hot.
How you like-
So
how you like
lots
driving?
of people will
How far
honk
should
at
you put Corey from the fulcrum
I like
to
it. It's fun.
Yeah.
balance the seesaw?
You drive like everywhere. Do you have your own car, or do you?
Do
use
the
your parents'?
problem, solve the problem.
We have
get
an
an
extra
answer.
family
How do
car,
you do without
but no one else is
calculator?
home, so that's
You don't have a calculator?
and
Well,
it's
not-
baby blue, and so it's really girly.
Right.
You could do it without a
Now you're making
calculator.
me do it.
Does your mom like get you to go drive everywhere like my mom does? Oh, it's like, hey, go get this, go get that. We have little brothers and sisters up, so she's got.
When she needs something, it's like something random, like I need this certain color of paint up in Leonardtown, and so she goes and gets it herself.
Oh.
And I don't like using her PJ's card all alone because I always feel like I'd be evil by signing her name and forging my picture. So I just cover my pic. And anyway, so no, I don't do errands
Wait,
for her.
so
Yeah,
is the
I
whole
use my mom's
seesaw
credit
5
card.
meters or just half
Cause she
of it?
just makes me.
5 meters.
Like gas, getting
The whole
gas.
Yeah.
I just make my dad
seasaw's
come
5,
with me
and
when I
the
get
cats
gas.
are right at the end.
Okay.
She's giving you her credit card. She's like,
I think it'd be. Well, he's
I need
4,
something.
so
whoa. What? That was weird.
it'd be pretty
Watch.
close to the center. Like,
Maybe I can see through it.
wait, how long is the board?
Did you
It's
see that?
it's 2.5 on either side.
Okay, I was
Did you see
missing that.
his-
No, I wasn't.
Right now. No, put
I
it down on it.
think class is over.
Isn't it so weird? Look, and it's just like